Okay, so yesterday we kind of did a discovery lesson where we took a look at our unit circle, and from that we produced the graphs of sine and cosine. All right. Now, hopefully you're familiar with sine and cosine from geometry. I think you should have talked about it a little in Algebra 2 in reference to the unit circle. So that's where we're going to kind of start off. We're going to pick up from going into trigonometry. So today we are going to exclusively look at the unit circle. Now, this isn't the only application of trigonometry, right? You learned about SOHCAHTOA, sine, cosine, tangent for your triangle side relationships. We'll get to that eventually, right? And actually maybe a little bit today or tomorrow. But trigonometry has uses in a lot of real life problems and examples and just in general. So here we have, again, the unit circle, right? So again, we get the unit circle from the equation x squared plus y squared equals 1. So we're specifically going to look at central angles today. So we have theta. Theta is a real number. And we're going to have some point, xy, which is on the unit circle, and it corresponds to theta. All right, so wherever our x and y is, that x and y is wherever our theta tells it to be, pretty much, right? So if our theta was, maybe 20 degrees, or, pi over 4 radians, whatever it may be, you have your corresponding coordinates, okay? And they're going to be on this unit circle. So with yesterday's lesson and the manipulative I gave you on the Google Classroom, what we looked at yesterday when we went around the circle and we mapped out the graphs, we figured out that the sine of theta corresponds to the y coordinate of that point, right? So you have your unit circle, you have some angle, and if I want to find the sine of that angle, well, I can just go to the y value of that point. And similarly, the cosine of that angle is represented by the x value of that point on the unit circle. So no matter where this angle is, if you're given an angle between 0 and 360 degrees, you can map it out on the unit circle and you can find its coordinate point. So those are our two most basic trig functions. What happened to my pencil? That's weird. Okay. Sine and cosine. Now, altogether, there are 6 trig functions, 6 basic trig functions before we get into, fancy stuff like inverse operations. And the other 4 we get from our relationship with sine and cosine. So the next trig function that we have, there it is tangent. Okay, we know from geometry, hopefully we remember, that the tangent can be represented by sine over cosine. So since we have values for sine and cosine here, I can substitute in y for the sine and x for the cosine. So if I wanted to find the tangent of an angle using the unit circle, it would be the proportion of the y variable, of the y coordinate over the x coordinate. Okay, and again, we get that from our original trig relationship, tan is equal to sine over cosine. Now, the other 3 are directly related to one of our original 3. Okay, so we also have cosecant, which was the, I don't want to say inverse, but the reciprocal of sine, right? Cosecant is 1 over sine. So on the unit circle, if I want to find cosecant of my angle, it's just going to be 1 over y. Okay, since we flip, right, 1 over sine, I put 1 over y. Then we have secant, which is the reciprocal of cosine. So that's going to get us 1 over x. And we have finally cotangent, which is the reciprocal of this. So that's going to be x over y. All right, so if we have the unit circle, we can find the value of any of the 6 trig functions just by looking at the coordinates of the corresponding point. So the way it is broken up, we have in each quadrant, so in this part, okay, other than the x and y axis themselves, okay, so there, obviously we have the sine of 0 degrees is 0. The cosine of 0 degrees is 1, right? And you can go around like that. And that's one of the reasons tangent and cotangent have some undefined answers, right? If you've ever typed into a calculator the tangent of 90 degrees, that would get you an error, okay? And if you looked at the graphs, and we'll do that eventually, they will be asymptotes at 90 degrees, right? That's because if we evaluate it, it is the y over x. Well, my y is 1, my x is 0. I had to have 1 divided by 0, right? And we can't do that. We can never divide by 0. So with these come some restrictions because we may have 0 in the denominator, right? Sine and cosine, those are always continuous. You'll always find a value for those. Now, anytime we're using the unit circle, okay, I'm not expecting you to memorize this. All right, so I'll put a copy of this up on our Google Classroom. If you have one saved for yourself, please feel free to use this. But this is kind of how it's laid out. So here we start at 0 degrees, right? Then we break it up, each section, into 3 parts. So first we have a 30-degree angle, then we have a 45-degree angle, then we have a 60-degree angle. All right, so that is the pattern that we take as we go along. So here we have now 90 degrees. Well, from the 90, I do 30 degrees over, which is 120, right? So from there to there would be 30 degrees. That's really thick. You can't really see that. Sorry. From 90 to 135 is 45 degrees. And then from 90 to 150 would be the 60 degrees. Okay. And again, from 180, we follow the same pattern. From 270, we follow the same pattern. So that's how we get these reference angles here. Now, on the edges where the coordinate points are, you'll see here that we have all of our points, right? Now, other than 0, 90, 180, 270, okay, or, it also gives you the radians here. So I like this version because it gives you everything, right? 90 is 2 pi, 80 is pi, 270, 3 pi over 2. And each one of these, it gives you the conversion. Okay, other than the straight lines where you get 1 and 0, you notice there's a lot of radicals, okay? And other than 1/2, every other answer is a radical. One other thing to notice too, though, is a lot of these kind of match up. So here for 30 degrees, we have √3 over 2, comma 1/2. And I'll explain where we get these numbers from exactly in a second. But then over here, I have negative 1/2 √3 over 2, right? Here I have negative √3 over 2, 1/2. Here I have 1/2 √3 over 2. And we can kind of see that pattern, a combination of those two, happens for our 30 and 60 degree reference angles. So 30 and 60, 120, 150. Okay. And then always for the 45, we have this root 2 over 2. Root 2 over 2, but this one's negative because we're over here on the left side. Here they're both negative because we're down here in the third quadrant. And here the y is negative because we are in the fourth quadrant. We get these values from our special right triangles. Do you guys remember special right triangles from geometry? Anybody? Yes or no? It's okay if you say no.
I kind of remember them. Not a lot, though.
You remember hearing the name special right triangles?
Yeah, isn't it with like 3 numbers? I think.
Right, right. Okay, there are 2 special right triangles in right. We classify them using 3 numbers, and those 3 numbers are the angles of the triangles. So the first is an isosceles triangle of 45, 45, 90. So obviously you have the 90 degrees there, and then both of these are 45 degrees. And then you have the 30, 60, 90, which is another right triangle with the 90 degrees there. And we have the 30 degrees and the 60. Now, with these 2 triangles, these are special right triangles because the relationship of the sides of these triangles is always the same. So with this, okay, if I set up a triangle in my unit circle, right, I could do that anywhere. Wherever my angle is, I could set up a right triangle, okay? And that's what we use for those reference angles that we saw on the unit circle. Now, with all of these, my hypotenuse is always going to be 1 because it is the unit circle and the radius is always 1. So for both of these, I have 1 as a hypotenuse. Now, it's always the relationship here. If this is 1, then hold on. One second. Well, oh, hold on. I gotta think for a second. I'm having a brain fart. Okay, so these are the relationships between the sides. Okay, so if we called this one and this one, then this would be the square root of 2. Now that's true for any right 45, 45, 90 triangle. So what we do is we say, if I make this one, then this would be 1 over root 2. This would be 1 over root 2. But in math, we don't like square roots in the denominator. So what we do is we multiply top and bottom by root 2, and we get root 2 over 2. Okay, here for our 30, 60, 90 degree triangle, we always have this relationship, right? So again, I am making this 1. So this is going to be 1/2, and this is going to be root 3 over 2. Now, hopefully these numbers, even though we just looked at it, look familiar, right? I have root 2 and root 2. I have root 3 over 2 and 1/2. going back to my unit circle, okay, we see those numbers there. So all of these values are derived from our special right triangles. Okay, so in the unit circle, no matter where our angle is, okay, I'm either going to try to set up a 45, 45 triangle in the unit circle, okay, and if that's the case, then like we saw, our coordinates are going to be root 2 over 2, okay, and the positive or negative just depends on which 45-degree angle we're looking at, okay, so if I'm looking at the normal 45, everything's positive. If I'm looking at 135, okay, well, that would be 90 plus 45, so I'd be able to set up a, make it purple. Okay, so if I, oh, that's a really crappy line. Okay, this would be a 45-45-degree triangle, but flipped over on this side. Okay, over here, the same thing. If I follow this 225, oh boy, that's just sloppy. Okay, again, if these lines weren't wavy, we'd have another 45-45-degree angle. Okay, and then the 30 and the 60 are just the 30, 60, 90 triangle put in its specific spot. Okay, so any questions about that so far? About where we get those numbers from? All right, so let's take a look at some actual examples. All right, so we're going to find all 6 trig values of the angle 5 pi over 4. All right, so I want to know what is sine of 5 pi over 4, what is cosine 5 pi over 4, and then from there, we can figure out the rest. All right, so for now, like I said, you have the unit circle at your disposal. So you would reference that, and you would find 5 pi over 4. Okay, so you go around for the radians, and you see, okay, here is 5 pi over 4. Right? If they asked you for degrees, right here, you'd be able to give it as 225 degrees. So for the sine and cosine, you're just picking out the x and the y value. Luckily here, they're both the same. Okay, so both sine of 5 pi over 4 and cosine of 5 pi over 4 gets us negative root 2 over 2. Okay, because this is our y value and this is our x value. They just happen to be the same. Now for the other ones, okay, there's going to be a little bit of work, but mostly it's just simplifying and getting rid of square roots in the denominator. Okay, so that's the main thing here. We do not want a square root in the denominator. So for tangent, of 5 pi over 4, well, we know that tangent is the sine over cosine, or the y over x. So I'm going to write it negative root 2 over 2 over negative root 2 over 2. All right, well, I mean, without thinking about it too much, without, I'm dividing fractions, so usually, we have to keep, change, flip. But these two are exactly the same, right? Negative root 2 over 2, negative root 2 over 2. So this simplifies to 1. Okay, and it's going to be a positive 1 because they're both negative, so that changes the sign to positive. And that was pretty straightforward. Now, from that, cotangent is also going to be pretty simple because it's 1 over our tangent, which is 1. So the cotangent is also just 1. The inverse of sine, we said, was cosecant. Right? So what I'm doing is I'm flipping this. So this is going to stay negative, but now it's going to be 2 over root 2. Again, we don't want that root 2 in the denominator. Okay, so I'm going to do everything I can to get rid of it. So we multiply top and bottom by the square root of 2. In the denominator, the square root of 2 times the square root of 2 is 2, right? Or it would be the square root of 4, and the square root of 4 is 2. In the numerator, these two are separate, so we're just going to put 2 times the square root of 2, right? And it's negative. We bring the negative along. And we can simplify further. The square root of 2, these 2's divide out. So the cosecant is the negative square root of 2. And because cosine is the same as sine, then we can say that the secant will be the same as cosecant, negative square root of 2. All right, let's do one more. All right, we're going to do pi over 3. Find the 6 trig functions for pi over 3. Right, so we reference pi over 3, so that would be over here, 60 degrees. So I'm looking at now 1/2 and root 3 over 2. All right, so I'm going to move this to the side so we still have that. All right, so again, sine and cosine are your simplest. You're just looking at the x and y values. The sine is the y value, so the sine is root 3 over 2. The cosine is the x value, 1 over 2. Now for tangent, okay, it's going to be root 3 over 2 over 1/2. All right, so here, because they're different, they're not the same, I'm going to do keep, change, flip. So anytime we have fractions and we're dividing those fractions, right, we keep the top 3/2, we change division to multiplication, and we flip this, so now it's not 1/2, it's 2 over 1. And multiplying these together, I'm left with the square root of 3. Cotangent, okay, is going to be 1 over the square root of 3. So if you notice, this is going to happen often. All right, so when we have this, I have just a little trick. This is always how it works. Bring the square root to the top and remove it from the denominator. Okay, so bring whatever's here into the numerator, and then just get rid of the square root in the denominator. All right, so I did what I did up here, okay, but here I'm giving you a little shortcut, right, because this is, you know, it saves you a minute, not too much. The cosecant. All right, well, I'm going to flip this now, 2 over root 3. So I'm going to do the same thing, okay? So I'm going to bring the square root 3 in the top, but I have that 2 up there, and then I get rid of the radical in the denominator. And then the secant, I flip this. Well, that's easy. That's just going to be 2. All right, so here we can calculate all 6 trig functions with close to minimal effort. All right, there is a little math involved, but really you're just picking your x and y and you're manipulating them. Any questions?